So I'm Sophie Wilson. I'm variously known for making things. My current role is I design firepath processors at Broadcom. With Steve Ferber, I was responsible for designing the very first ARM, or in fact the first 3 or 4 of them. We had involvement up to ARM 11, I think, and that was about the last one we actually participated in the design of. When ARM was formed, Steve went off to Manchester to become a learned professor of computer science and sit in a chair, and I stayed at Acorn doing software-y things. But now I design processors like everybody else. At the time, Acorn made and sold reasonably successfully machines powered by the 6502 microprocessor, running at 2 megahertz faster than it was used in other computers. Acorn had won the contract from the BBC to design and build the BBC microcomputer, and that prompted rapid expansion of Acorn, so we started looking at what to do next. When the BBC computer was designed, there was a quandary because different forces at Acorn wanted a different machine. Herman Hauser, the director of Acorn, overall big chief, he wanted a computer to do office automation with. Chris Curry wanted a successor to the Atom. He wanted a home computer, a games type machine. Andy Hopper, who was a director of Acorn as well, he wanted a scientific computer, and Steve and I just wanted something that we'd be happy making. So the solution to this eventually was to design the BBC microcomputer as a multiprocessor computer. So the bit that everybody knows, the original beige box, is essentially the I/O processor for everything else. It's got all the I/O stuff, and it has a special connector underneath it and a special interface called the tube, which joins second processors to it, where the second processors are in charge, and the BBC computer just becomes a language processor, an I/O processor to the language processor. So doing that, we were able to quickly implement something, because you could build a computer without any I/O. You just had to build something with enough memory to start up and run the tube protocols, and everything else was then taken care of by the I/O processor. And running the tube protocols is fairly simple. So we could build a 286, an 8086, a 68000, a National Semiconductor's 32016, and see what happened with those machines. And each one we implemented would come with a large set of marketing claims from its manufacturers saying how wonderful it was and how it would transform our life. So all of these machines were running without a cache. So their memory systems were responsible for all the performance. There was no cache, so you're fetching instructions directly from memory, reading and writing directly from memory. And we formulated a rule as we tested these things that the performance of all these processors, no matter what the claims were of how wonderful the instruction set was, that performance was directly related to the memory bandwidth. So if we built a 6502 processor and we ran it at 4 megahertz and it had a 1 byte wide bus, and we could make the bus run at 4 megahertz, which was the same speed as the memory system inside a BBC Micro, then we'd get our sort of standard unit of performance. And if we got a 68000, say, it ran at 8 megahertz. So you'd think, aha, it's going to go much faster because it runs at 8 megahertz. But it has a bus that takes 4 clock cycles instead of 1. So the bus runs at only 2 megahertz, and it happens to be 2 bytes wide. So that also comes out to 4 megabytes per second, just like the 6502 did. And I won't bore you with the details of what happens on an 8286 and an NS32016, but you essentially ended up with machines with the same bus bandwidth. And okay, you say, well, the 68,000 16-bit processor, it has 16-bit instructions. Surely that's going to be more powerful. It may only be able to fetch half the number of instructions per microsecond as the 6502 can fetch, but they're working on bigger chunks, and therefore it will be better. And long story short, it isn't. The little instructions, the 8-bit instructions of a 6502, it can get through 4 million of them per second, and a 68,000, it seems cruel to single it out. Let's say an NS32016 National Semiconductors processor, it can only fetch 2 million instructions per second, and they're dealing with bigger things, but it's not enough to make up the difference. Particularly when you get down to branch instructions and things like that, it really isn't enough to make up the difference. Also, these processors were built differently. So the big 16-bit processors, I say big now, but anyway, that's how we thought of them then, they were microprogrammed. So they take 4 clock cycles to do the simplest thing. The 6502 wasn't microprogrammed. It had a simple 2-stage pipeline, and it would fetch an instruction in one cycle, decode and execute it in the next cycle, and then do another one. So it actually got through its instructions much more quickly, did much better. So by the time you looked at it from the outside, not knowing what was going on, all of these things performed the same. And that seemed to be a trouble to us, because we knew how to design much faster memory systems. And could these big processors, 68,000s, 8286s and NS32016s, actually use them? No, they couldn't. So we were stymied for quite a long time. And then 2 different things happened. The first one was we flew out to America to go and visit the people who designed the 6502. So this is Western Design Center in Phoenix, Arizona. So you land in the middle of a desert and wander around in very pleasant places. And we were looking for a big industrial science park type of thing on our way to Western Design Center. And where we actually ended up was in a small cul-de-sac on the outside of Phoenix with bungalows. And they had 2 bungalows, and some electronic engineers and some grad students were designing processors. And they were designing them without computer automation. So they were sitting at large drawing boards with big pieces of translucent paper on them, and they were sticking rubylith tape onto the drawing board to say where some metallization or polysilicon would go. And that's how the 6502 was designed. They were devising the next generation, a 16-bit descendant of the 6502, the 65SC816. Snappy name, but there we are. Acorn would go on to use that processor, but we weren't really impressed, and it didn't get us out of our quandary of what do you do to get something better. So we thought about it for quite a while. And then the second thing happened. IBM, Stanford University, Berkeley University in the States had all been researching different ways to design a microprocessor, the so-called reduced instruction set computer. And they'd all published papers on it. Andy Hopper put those papers on my desk. And what was most striking about these papers was the internals of a processor became much simpler. What had been reduced wasn't the instruction set, it was the complexity. So they're reduced complexity instruction set computers, but that's not a snappy acronym. So the complexity of implementing an instruction set was much simpler in RISC. So with that and our experience of going to see Western Design Centre, we thought, well, if those guys can design a complicated instruction set computer, surely we can design a reduced complexity one. And Herman got convinced quite easily. He's that sort of person. And so Project A was born, build our own microprocessor. In setting off to design our own processor, we needed to keep our eyes on the prize. We needed to know what we were doing. So what we wanted to do was build a processor where we could basically get pretty much the same performance as a BBC Micro, but writing in a high-level language. So on the BBC Micro, practically everything had to be written in machine code from scratch by experts. And you got people like David Braben and Ian Bell writing 3D space trading games like Elite on that platform. But they had to be genius-level people like David Braben and Ian Bell. And we'd rather like ordinary people to be able to do the same sorts of things. So we needed to get a lot more performance. And RISC promised us some of that, but we also wanted performance for the masses. And our slogan internally was MIPS for the masses. Millions of instructions per second for masses of people. We wanted to build a small, cheap processor that ran 10x or more faster than existing processors. So slogans are very useful because they make it simple to think about. You know what you're doing. But without that piece of analysis, I think things would have turned out very differently, because certainly what Berkeley designed, what Stanford designed, were not MIPS for the masses. They were high-performance workstation processor replacements. That's what they were aiming at. And having a different aim, you end up with a different thing. So part of MIPS for the masses is being able to get into a cheap package, being able to get into a cheap box with a cheap power supply without noticeable amounts of cooling or anything. So a lot of what people remember about early ARM processors is all to do with those things. The big key difference was we were a commercial company who make and sell actual end-user computers, and we were designing a computer chip for ourselves. So the first thing we did was not to design a single computer chip. We designed 4 at once. So Project A at Acorn was design ARM1, sure, everybody knows that bit, but we also designed a video controller, I/O controller, and memory controller, and made the whole 4-chip set work together harmoniously. So it was all about being able to implement cheap computers in the future with the chipset. It was, as I said earlier, it was about making sure that power requirements, cooling requirements didn't get in the way. We wanted to put everything in cheap plastic packages, so we needed to make sure we didn't use too much power. So competing devices came in expensive ceramic packages, and some of them had heat sinks on them and all sorts of nastiness like that. But for us, the price difference between that sort of solution and a cheap plastic package with no cooling was really, really important. And we kind of overachieved that a little bit. So we wanted to get into a plastic package with somewhere between 1 to 5 watts power dissipation, which is what it could handle. Steve, in implementing the microarchitecture and all its sub-blocks, didn't have any engineering tools that were particularly good at estimating power. Most of building ARM1 was done without tools. So we wrote our own behavioral models, cycle accurate simulators, register transfer models of the processor. there weren't any tools to build microprocessors with at the time, or to build complicated chips. The processor was laid out, or indeed all the chips were laid out by hand with some degree of automation, TCL scripts. They were laid out by hand on computers rather than by hand on big drawing boards like Western Design Centre were doing, but still laid out by hand. So Steve was very, very careful in his estimates of how much power each block would use. We could SPICE simulate transistors when we got down to that level, but how the power built up in the processor, we had no idea. So overall, we kind of overshot the power target a little bit and hit 0.1 watts instead of 1 watt, which would later become an enormous advantage. So we talked a lot. So the instruction set and the microarchitecture were co-designed by Steve and myself, with Herman as an interested listener. We'd walk down the road to the Robin Hood, talking about what we'd done, what stage things were at. We'd discuss how to do instructions, and if I wanted an instruction in the instruction set that Steve couldn't work out how to make the microarchitecture work, we couldn't have it. Whereas if we could work out a microarchitecture, then we could have it. So there's no decrement and compare against zero, which I wanted badly for density of loop work, but there is conditional execution of all instructions, and there is load multiple and store multiple in ARM1, because we could work out how to do those things. There were things that we thought were very dicey. So in other machines, there were things like branch with execute, and we didn't like that as a concept. We didn't see how it went forward when you changed your processor. And we didn't see how they made it truly safe over interrupts. So we didn't put things like that in. It was a matter of designing it like that. Now, when you're designing it in your head and talking about it, it's easy to end up with the wrong impression. So we also followed all that talking up with ironclad models, so that we could really, really agree what we meant by things. So in designing the instruction set, I also wrote an instruction set simulator. I wrote it in machine code for the 6502, and it was a precise representation of how the instructions should work. Steve made his microarchitecture work by writing an event-based simulator in BBC Basic and using that to make a microarchitecture simulator of how the processor did things. And then a team of people led by me wrote verification suites to prove that everything worked the way we thought it did. And we'd run the verification suites on my behavioural model first to prove everything out there, then on Steve's register transfer level model, which was much slower. And then when we had all the RTL of the processor, well, we didn't have any RTL in those days. When we had the transistors extracted back into SPICE, we'd run SPICE simulations on a subset of the tests to prove that all of that worked too. So talking a lot, writing things down, and then writing precise models of what we wanted was how we controlled the internals of the project. I think every chip that we did worked first time correctly up to about ARM8. Getting things right by simulation before we made things really mattered. Well, of course, nowadays you think, oh, yes, we'll just port a compiler and we've got all these amazing tools. Well, we didn't have any compilers, so ARM was designed to accommodate all the possible future compilers we could think of. Nowadays, people tend to optimize their work just to run C, say, but ARM was designed to run C, Prolog, Fortran, BCPL, BBC Basic, as it happens, and to do this from an assembler level view as well as from a high-level language view. Much of the compilers would not be written by the time we taped out. I think we only had the BCPL compiler working at tape out, but we taped out even without verifying and fully debugging that. So yes, it's difficult to imagine this, but we've been there before. When we first started making machines at Acorn, we had no tools at all. So everything was write assembly language down on paper, hand translate that to binary patterns and feed that into computers. That's how we started. And one Christmas I wrote a thing that was an assembler because I was getting very bored of doing it by hand. And then the next Christmas I wrote BBC Basic. Well, I wrote Acorn Basic version 1. Different people want different things. So everything is a trade-off. So that the classic version of a trade-off is you can have it fast, cheap, or good. Pick any two. You don't get to have everything. If you want it fast, if you want it to be developed quickly, then probably quality will suffer, or it won't be cheap to develop it quickly. You can't have everything. So for designing processors, the number of trade-offs is vastly increased. The things people care about are, well, some people care about really high performance. Some people will care about performance efficiency, and those are two different things with very different solutions. Some people will care about its physical size. I mean, somebody who has to put 1,000 of them onto a chip will worry a lot about its size, where somebody who only has to put 4 of them onto a chip won't care quite as much. Some people really don't care about instruction set density, and for some people it's life, the universe, and everything. Development time. Can you design a successor? This is something that people don't think about enough when they're designing something. What did you do? Does it leave holes for a successor to come? Is there something natural about it, or is it a dead end? So those things matter as well. And you just can't have them all at once. So different people want different things. So if you're designing a system that's wholly on chip, then instruction set size matters hugely. You're going to have all your firmware living on the chip with your processor. It's worth complicating your processor to make your firmware smaller, because at that space you're going to have to pay for both in power and in die area. So that class of person cares enormously about instruction set density. Then there are the people who want physical security. One of my oldest anecdotes about Acorn is that Acorn's first customers wanted physical security for their designs. So Ace Coin Equipment in Wales approached Acorn, back when it was called CPU Limited, Cambridge Processor Unit, to put electronics inside the fruit machine, i.e. take away all its relays and other switch controls and replace them with purely electronic controls. And we did that. Rather, Chris Turner and Steve Ferber did that. And then Ace Coin Equipment had a request. We know that there are these piezoelectric lighters going round, they said, and people are approaching our fruit machines in pubs and snapping the piezoelectric lighter to cause interference. And it is now a requirement for anything that's you, Acorn, give to us, that it's secure against that. So that's physical security. And I had to engineer at a moment's notice with the contents of Chris Curry's drawer of interesting chips, a wideband radio receiver to detect the interference of a piezoelectric lighter and forcibly shut down the computer and stop it paying out. So people who are worried about physical security have a completely different set of worries, and they hate complex interfaces, they hate anything that could be disrupted, and they hate anything that has implementation defined next to it in the instruction manual. Guiding principle that's worked best for me is you've got to keep the implementation team happy. It's no good setting yourself a target that the team aren't happy about. You might get through that target, but the next one your team will leave. So building a long-lived team and working with people for a long period of time is a massive help to any of these class of difficult problems. When you come to engineer an answer to a particular problem, you've always got to be asking yourself, is there a successor to this, or have I designed myself into a corner? Am I doing something that is a sticking plaster over the problem and I should design it a different way? And of course, can I keep the team happy? If you know it with clarity and everybody's agreed about it and worked out how to, worked out a whole sheaf of possible solutions to the problems, then it does come down to keeping the team happy. That's the best solution of all. It doesn't usually work out like that. You can't usually get a single solution that works for everybody. You've got almost certainly multiple clients with somewhat dissimilar needs. Even if, say, all your clients agree that on-chip memory for storing the program is important and therefore instruction set size really, really matters, some people will be different and want different things. Some people will care about the physical security thing and they'll want a whole raft of ECC stuff that the other people don't want to pay for, etc. A suitable anecdote is how to build a racing car. Make it as powerful as you can with as strong brakes as you can and then add lightness. So the saying is, perfection is achieved not when nothing can be added, but when nothing can be taken away. When you have a design that perfectly answers all its immediate needs and doesn't go beyond that in carrying weight to answer needs that aren't real. And of course that does mean you've got to be really careful in establishing the needs. You sort of recognise when things can't be simplified anymore, recognise when it's beginning to look ugly and broken. You recognise when other people should be consulted about something. When the team as a whole isn't happy, then maybe you ought to change things. And of course you're designing things that, like ARM1, have to be verified. So you may have a perfect engineering solution, but if the verification team can't work out how to verify it, it's not a solution. So when we designed ARM1, we built it in a 3-micron technology. Back in the days when 3-micron meant something, it was the actual gate length of a transistor. So a transistor isn't 3 microns across, the gate length is 3 microns and a transistor is about 10 microns across. It's comparatively huge. In those days, transistors were quite expensive. I mean, amassing as many as 27,000 of them on ARM2 or 25,000 of them on ARM1 and getting them in one space, you ended up with something that was quite large, about 60 square millimeters. Transistors were quite slow. Metal was almost infinitely fast. So solutions to things like barrel shifters were very different from nowadays, when metal is really slow and transistors are really, really fast. Design tools influence things a lot. ARM1 was designed with VLSI technologies, layout tools, so they were proprietary. Everything was designed at the transistor level. You weren't writing in a high-level manner and having it compiled to the silicon for you. So the complexity of things you could undertake was quite limited. And a lot of scripting was done on ARM1 to replicate cells. So somebody would design a register cell, a 1-bit cell for one of the registers, and then it'd be replicated by a TCL script over the data path. So everything was in a very primitive era compared to modern synthesizers, silicon compilers, so-called, being able to do all the layout themselves, well, if you pay enough money for one. The change in routing also matters. ARM was laid out, ARM1 was laid out by hand, and just routing the buses around the place set a lot of the parameters for the layout, because we only had a few layers of metal. And with a modern process, you've got, 15 layers of metal. You can arrange that the power tracks don't get in the way of the signal tracks and all that sort of thing. The penalty, of course, is that your metal's got very slow per scaled unit length, which doesn't help. Power's always been an issue. So we're talking of an era where machines have got tens of thousands of times faster than they used to be. Most of that speed up is not coming from instruction set design and microarchitecture innovation. There's only about a factor of 10 coming from those things. The rest of it has come simply from transistors getting smaller and faster. So that has two effects. They get faster, so instead of clocking at a few megahertz, processors clock at a few gigahertz, and we can have many more of them. So instead of having very simple in-order designs or small amounts of pipelining, we can have massively complex out-of-order designs with very deep and fast pipelines. And of course that makes it a lot more complicated to reason about the processor and to find the faults in it. So there are two aspects to security, one of which I've already touched on, physical security. You want to make sure that nobody can subvert your system, even if they're coming at it with an electric cattle prod. And that's really quite hard, and it's still a very specialist application. Even stopping people opening your chip and stealing secrets from it is still really quite hard. Then there's security at a distance, stopping people, if they've got the rights to run code on your machine, from doing anything harmful. And that's very difficult because, well, A, you shouldn't be doing that. Remote procedure calls were a big mistake. Giving people the ability to run processes on your computer when you don't control what that was is a really big mistake for security. You don't want to do that. So the physically secure people would say, over my dead body, do you get to run any programs that we didn't already verify? It's just too much of a pain. If you are going to do that, then you're into some horrible worlds where a lot of design techniques have information leaks in them, and this stuff is very complicated. Practically every microarchitectural mechanism that has been invented to make processors go faster has a theoretical information leak, which nowadays somebody has thought about how to make the most of. So your branch predictor, your caches are all potentially vulnerabilities if you're concerned about security. So obviously ARM1 came about because we were designing a multiprocessor. It only had 2 processors in it, but it was a multiprocessor anyway. And we committed one of those things that you only read about after the event in textbooks. So the first implementation of the tube has a flip-flop synchronizer failure in it. So once every uncountably long number of actuations, we would get synchronizer failure in our flip-flop, and the signal, instead of toggling smoothly from one state to the other and back and so on, would just oscillate for a while and everything would go haywire. In the Silver building at Acorn Fulbourn Road, which is approximately just over there, Steve had to set up a whole massive number of processors running a simple test program running the tube to catch it, and the solution to designing it out is fairly simple once you know it's happening. Now, any multiple access, any arbitration, has the same types of vulnerability. Synchronizer failure with very fast transistors remains a possibility, even if it gets more remote. Designing things with single clock zone, single voltage island, single power island, single clock island, makes a lot of things simpler, but you've always got an edge, you've always got talking to somebody else. So there are all sorts of failures that can happen when multiple things are happening. And even if you get all the hardware right, then the software that's built on top of it will have problems too. So building such systems and making sure they can be diagnosed when they inevitably go wrong is tough and leads to very complicated solutions, and very complicated solutions usually don't survive very long. You try and get it right. You try and get everybody be happy with the ideas that are behind it all, and you try and have a plan B. And when you notice that you've designed yourself into a corner, you have the strength to admit it and start all over again. So I might say I've been designing firepath processors since 1990, which is when I started doing it. They were first implemented on working silicon in 2000, and descendants of that implementation lasted all through to about 2012, when we decided that that implementation of a firepath wasn't right and we needed to tear it down and build a different one. And it's how you take stuff forward when you realise you have got to tear it down and build a different one. If you've got programming at the level of C, that's going to survive. But if you've got programming in machine code, how can that survive? How can your RTL come forward from your old dead-ended version into your new one? There's a whole lot of very tricky compromises. So Gordon Moore, while at Intel, made an observation about the number of transistors he could economically get on a piece of silicon. And it increased. When he first made the observation, he said you could get twice the number of working transistors economically on a piece of silicon every year. over time it was backed off to every 2 years. This didn't matter very much at the very beginnings, but when we got to integrated circuits, so things that used many transistors, it began to matter quite a lot. And a steering company was set up to ensure that Moore's law worked. So the ITRS, International Technology Roadmap for Semiconductors, was a body that steered development of silicon manufacturing technology to fulfill Moore's law. ITRS has now closed down, but there's IRDS, the International Roadmap for Devices and Semiconductors, which is still trying to fulfill Moore's law. Now, it's a law about economics, so it doesn't merely matter that you can make smaller, better, faster transistors with your latest dum-de-dum-de-dum process. It matters that you can make them economically. So in some senses, Moore's law stopped at about a 28 nanometer process, because after that, transistors still got smaller, better, faster, but they didn't get cheaper. You could have more of them in a small space, but the cost of a processed wafer was rising. So at 28 nanometer, a processed wafer was about $3,000. Now it's somewhere north of $20,000. And although we get many more transistors with the processors labelled N7, N5, the label doesn't mean that there's anything at all remotely that's 5 nanometers in size on there. A transistor is about 50 nanometers across. So it's many times bigger than you might have thought. But that's fair enough, because the old label, the 3 micron label for ARM1, a transistor was still many times bigger. Those transistors are costing so much more. It's so complex to make the things. So back on 28 nanometers, you'd probably get away with single exposure on each mask. You probably only had about 30 or 40 layers to make the thing work, depending on how worried you were about various performance and power trade-offs. On 5 nanometer, you've got a mixture of DUV, deep ultraviolet exposure, and EUV, extreme ultraviolet exposure, 193 nanometers or 13 nanometer wavelength light. And you'll notice both of those numbers are quite a lot larger than the feature size. So 28 nanometer process made with DUV, you're using tricks to resolve smaller features on the die. And those tricks are things like digital pre-distortion of the mask before it's exposed to try and overcome diffraction effects. And as you made things smaller with DUV, and we used DUV all the way down to processors labelled 10, which doesn't of course mean 10 nanometer is on there, but they're labelled 10. So you're trying to build smaller and smaller things with DUV, and you have to use multiple exposures of each mask. So self-aligned quadruple patterned processors are in use in many of the layers on 10 and on 7 and on 5. And then EUV, because it's so fantastically expensive, is used for just a few layers where it really, really matters to get the precision. So all of that stuff is really, really expensive to do. And so the cost per transistor is actually rising and has been rising for quite a while. So in that sense, Moore's law is dead, dead, dead and dead, but we can still have smaller, faster, cheaper transistors. Another law along the way that died, we used to have a lovely law about scaling. So as you made your transistors smaller, their threshold voltages dropped and their operating voltages dropped. So you had the beauty of getting a smaller transistor that used V squared less power. But that law hasn't been true for quite a while. ever since we got down to something like about 16 or 20, that really hasn't been true. We can't drop the voltages very much without giving up a lot of what makes a transistor a nice transistor. So the other law that affects everything that we do is Amdahl's law, and it really is a law. There's an equation, you can draw graphs. It's ironclad, and what it basically says is if you've got to accomplish a task, that then there are some portions of that task that require that they be done sequentially, and then other portions of the task can be done in parallel. And it's the sequential portion of the task that determines how much speed up you're going to get. And that speed up matters whether you're talking about out-of-order superscalar processors or multiprocessors or multi-computers or whatever. So it's not how parallel can you make your problem, it's how serial the remaining bit is that gets you. So Amdahl's law has massive consequences, and a lot of smartness is put into trying to avoid it. They're predictable changes, and they're of a piece with what's been happening in the past anyway. So I don't see any major surprises on the horizon. And obviously the field is changing quite a lot at the moment, in that we've always designed special purpose processors. So throughout everything that we've been talking about, we've said processors, but without being specific about whether we mean controllers, digital signal processors, graphics processors, knowledge processors, network acceleration processors. There are all sorts of things called processors, and they're evolving in slightly different ways because they do different things. And it's likely that there'll be future special purpose processor devices come along, but they'll be of a piece with what's gone before. When I grew up, it was quite common for things to be made by people you knew. I grew up in a house where my father had made most of the house's furniture, the bookshelves, bureaus, tables, chairs. He built a boat, he built a car. My mum had made the soft furnishings, most of our clothes, curtains, etc. My mum taught physics, and all the laboratory equipment in her physics lab we'd built by sitting as a family round the dining table and assembling multimeters and oscilloscopes and so on. So I grew up in a world where people made things. I made things. I made radios, and eventually I made computers. So there's a great deal of fun to be had in creating things. It's much harder nowadays. You live in a world populated by things made by people you don't know, that are relatively impervious to even understanding how they're assembled. So it's quite hard, but making things is really, really rewarding, and you can do it if you try. And you can start in simple ways by writing software and joining software projects. You can learn hardware. I learned hardware with soldering irons that burn your fingers, but you can learn hardware with out a soldering iron nowadays. Buy yourself an FPGA kit or a Raspberry Pi and learn how it all works. Because the thing about the electronics industry, semiconductor industry, the processor industry, whichever little facet of it you prefer to think about, is that it runs by people knowing how to make things, knowing how everything works. When you get an interview with a company, being able to demonstrate that you know how things work is what matters most of all. I have on occasion interviewed people for jobs, and it's amazing how many people apply at the company with impeccable CVs, and then you ask them to demonstrate their programming skills by writing a program, and they fall apart into a little heap. If you're a master of writing a program, knowing how to do it, working with other people is a good skill to add. So join maker communities, join people who are doing open source programming, join something and work with other people to make things and show you can do it.